Hey guys, so today we're going to be looking at how to solve problems using the Taylor series in a two-dimensional plane. So in this case, we're going to be looking at functions with two variables. So as you can see here, the formula for this is the one underlined in red, which contains two parts. A linear part, which is this part here, and a quadratic part, which is the second half here. So this formula looks a bit daunting because it's actually quite a long formula and there's just a lot of stuff going on there, especially with vectors and gradient notation, the Hessian matrix, and also there's a Jacobian. So in this case, the best way to approach these kind of problems is to break them up. So here we have underneath that is just the linear bit, which is simply just this first term here, just right before the half. So what we're going to do is we're going to evaluate the linear part at x using the function evaluated at the point P, in this case 0, 0, plus the Jacobian evaluated at the point P times x minus P. So the best way to always start these kind of problems off is to take all your partial derivatives. So the partial of x, or with respect to x, will just be e to the x cosine of y, and the partial of f with respect to y will be negative e to the x sine of y. So now we have our partials already evaluated of the function e to the x cos of y. Now we can go ahead and evaluate f of p. So f of p in this case is 0, 0 is just going to be 1 because e to the 0 is 1, cos of 0 is 1. F of 0, 0 equals e to the 0, which equals 1. And now, the next part, we can construct this Jacobian. So Jacobians are a matrix of partial derivatives, is the best way to kind of think about them. They take a function of Rn to Rm, I think is the definition for it. But in this case, it's best easy to think about Jacobian of f is equal to kind of the first derivative like this in a matrix, and basically converts it to a vector. So in this case, we can say our Jacobian will be e to the x cosine of y and negative e to the x sine of y. This column, the top column with respect to x and the bottom one with respect to y. Perfect. So now that we have our Jacobian, we can actually evaluate this at the point P. So jf at 0, 0 will be 1, and then sine of 0, 0, so just 1, 0. That's easy peasy. So now we've done both of these points, we can get on to this last part of the linear part, which is x minus p. So in this case, the vector x denoted with the expression x underline will just be a vector xy, and our point P 0, 0 from earlier. So we get x minus 0, y minus 0 as x minus p. So we're just left with the vector xy. And now this last part says the Jacobian times x minus p. So we can actually write this as 1, 0 times x, y. Now, if we want to multiply, we just are left with x using matrix multiplication. So now, if we add all of this together, our f of p was 1, and our Jacobian of f times our vectors x minus p was just x. So we're left with just 1 plus x. So our linear part approximates 1 plus x. Perfect. So this is the first part of calculating the quadratic part of the Taylor series expansion. So now what we're going to do is we're going to kind of move on to the second part, this part here. So this part looks a bit more complicated. There's a bit more going on here, including with the Hessian matrix, but we'll run through it now. All right, sweet. So this is the part that we're going to use now, is the quadratic part. So I've just run that part here. It starts from the plus half. So we have plus half times x minus x naught, and these are all vectors as well, I should say, times the Hessian matrix, which I'll go over once we get to that part, evaluated at the point x naught. Remember our point at x naught, 0, 0, times x minus x naught. Something to note as well is that here, where the transposed part, which is what this t means here, there's actually a dot product, which is something that I think the notation doesn't really cover quite easily unless you're familiar with like the transpose notation and whatnot. So we already know our partial derivatives with respect to z to the x cos of y, and with respect to y, it's negative e to the x sine of y. So the Hessian matrix is kind of like the Jacobian, except it evaluates at second order partial derivatives. So the second partial derivative with respect to the first one. So as you can kind of see, it's following the normal 1D Taylor series approximation where you keep taking the nth derivative. So in this case, the matrix is built like this: f of xx, f of xy, f of yx, and f of yy. Something to note as well is because since these partial derivatives are equivalent, you only have to calculate f of xx, f of xy, and f of yy, because you know that f of yx and f of xy are going to be equal. So in doing this, we can simply take these second order partial derivatives. This is the notation that I like to use. I don't typically use fxx because I like when the notation looks fancy. So with respect to x, it's just the same thing. And with respect to y, it is negative e to the x cos of y. And then we're going to find the partial derivatives of dx dy. So we're finding the partial derivative of x with respect to y. So in this case, e to the x cos of y is just negative e to the x sine of y. So as you can see in this matrix, there's a lot of symmetry. So now constructing our Hessian matrix following the diagram above, we can see this will be e to the x cosine of y, negative e to the x sine of y, and then the same thing here, and then with respect to y, it should be negative e to the x cosine of y. So with respect to x here, with respect to xy here, with respect to yx here, and then with respect to y here. So now we're just going to go ahead and unpack this all. So first, we should probably evaluate our Hessian matrix at the point x naught. So in this case, 0, 0, to just tidy up and simplify it. So h of f, the Hessian of f at 0, 0, will be e to the x cos of y. Cos of 0 is 1, e to the 0 is 1. It's sine, so it's 0, sine, so it's 0, and this will be negative 1. Perfect. So now we've constructed our Hessian matrix evaluated at the point 0, 0. So now we can kind of evaluate this all. So I just kind of like to leave the half out here, kind of times everything. So now we have our xy minus our point, so kind of like before. This is dotted with this matrix. And the Hessian multiplied by xy minus 0 minus 0. Boom. Just simplifying this. Get a vector like this. Dotted with this. Multiplied by xy. So it's easiest to do the matrix multiplication first. So in this case, we get the half xy dotted with, and then using matrix multiplication, we should get x negative y. Now using the dot product, we should get x squared minus y squared. That is all multiplied by half. So this means that the quadratic part is approximately equal to this. So now we have both a linear part, which is this part here, and also a quadratic part. So now we can actually just add these together because that's what the formula tells us to do. So our approximation of f of xy is 1 plus x plus half of x squared minus y squared. And I'll put up an image of what this actually looks like and how you can kind of see it in a 3D sense using Desmos. So that is how you use the Taylor expansion in 2 variables, using this formula here and how to break it up and how to kind of problem solve with stuff like that. So depending on kind of the function that you're given, it can take longer or be shorter perhaps, depending on what you're given. When you're typically given stuff with easy partial derivatives that kind of simplify down to 1 or 0, it doesn't take too long because you can evaluate stuff in your head pretty easily, assuming you know your cosine and sines of zeros. And yeah, awesome. So thank you for watching, and I'll see you guys in the next video.